So in general, we have seen that if we have a curve and we, without specifying it, assume that this curve y equals f of x was above the x-axis, what we did is we calculated the area under the curve, which we denoted by the integral from a to b of f of x dx. Now this s stands for sum, and it stands for sum of all areas of rectangles where is f of x dx. So roughly speaking, you have somewhere a rectangle whose width is dx and whose height is f of x. So this formula reminds us what we were supposed to do. And in a Riemann sum, we have seen that what this means is that you take limits as n goes to infinity of summation k from 1 to n of f of a plus k times what? b minus a divided by n times b minus a over n. Now, the sum stands for the sum over all the rectangles. This tells us how to find the point. This point is x sub k. Okay? This point is x sub k. Now, in particular, in this setup, we are picking the right-hand point and plugging the right-hand point into the function. Now, there is nothing special about putting in the right-hand point. What is this expressing? So how would you, if you have a curve, so this is A, this is B, the function is y equals f of x. How would you use the left-hand approximation by L sub, well, by n rectangles? So let's call it L sub n. And L sub n is designed as follows. So what you do is you pick the first point. That's the height of the first rectangle. Then this is going to be the height of the second rectangle. This is the height of the third rectangle. So we are picking heights for the first rectangle at the left-hand point, for the second rectangle at the left-hand point. We are always picking them at the left-hand point. What would have been the formula for L sub n if we're using left-hand approximation? You see, like when you look at this limit, you right away know that right-hand approximation was utilized. That means that we subdivided the interval AB into n equal chunks, and over each chunk we picked the leftmost point, sorry, the rightmost point here, right? So here in this setup we always picked the rightmost point of each interval segment. Now we can construct a Riemann sum by picking the left-hand point. What would be the formula? So first of all, summation, right? So we have summation of n rectangles. So that means k starts from something and goes to somewhere. Okay, go on. What is f of what?
b minus k, b minus a over n.
b minus a over n. This represents the width of one segment, correct? What more? What more do we need to do here? So the setup that I want is as follows again. Point is fed, then move to the right. The point is fed, then move to the right. You see, so you're using left-hand point. So that means what? Where do we start? A. You can start with B or A. That's up to you. Let's say we want to start from left to right. So let's start A. Then what? Plus K.
Over B minus A times T.
So why is that K times, right? So K times because we displace 1 unit, 2 units. We displace K units of this length. Does this make sense? Right? So this is just A, and then tells you how many lengths of segments do we need to displace. That's K. Here we have B minus A divided by N. Now the question, where does K start from and where does it end?
Starts from 1.
If it starts from 1, we get exactly the same thing. That's right-hand approximation.
Wait, from that graph? So start with A.
It has to start with A, which means K is equal to 0. And goes all the way to?
3.
Think about it, right? Here is the last segment. Here is B. We are going to pick this point. So what should K go to? Sorry? N minus 1. Okay? So that would be the left-hand approximation. So in general, we can have a partition where what we are using is, so here is first interval, and we can use just any arbitrary point as the height. Some arbitrary point for the height. Maybe this one. Maybe this time I decided to choose this point, the right-hand point of the interval. And maybe this time some point here. Okay, so that's just a typical approximation. So this would be marked as x1 star. x1 star indicates that x1 was picked to create the height for the rectangle 1. This would be x2 star, x3 star. This, in this case, x4 star, then x5 star. And what you have is, typically, you can say that the integral from a to b of f of x dx is approximately equal to the summation where k goes from 1 to n of f of some xk star. So that's basically, you see, here is x1 star. I put it in f, and that creates the altitude for my rectangle times delta x. And delta x, by the way, they don't have to all be of the same width. Delta x could be of different width. Maybe this is wider, the next one is a little narrower. That can happen, but as long as the widths diminish to 0, and as long as we create more rectangles, that should work fine. Okay? So you can sometimes just write that the integral from a, b, f of x dx is equal to limit as n goes to 0, to infinity, I'm sorry, and as maximum of delta xk so that tells you that you are forcing the widths of rectangles to go to 0 of any sum of the form k equal 1 to n f of xk star delta xk. Okay? So using this, basically just the understanding that really when we are doing integration, we are just summing over a bunch of rectangles gives us many properties of the integral. Okay? So let's consider properties of the integral. First of all, we give this mathematical formula its own light. We don't have to interpret it as area under the curve. So suppose we have a function that looks like this. It's no longer a curve over the x-axis, okay? So it's just some curve from A to B. So let's try to interpret what is the integral from A to B of f of x dx in terms of area. So if this is area 1, this is area 2, this is area 3. So let's see what happens, right? So the integral, its only interpretation is that it's the limit of the sum of rectangles whose altitude is f of x and whose width is dx. So let's see what's going to be the altitude. If I select a rectangle over here to test, what can you say about this rectangle? Height is positive and width is positive, right? So the rectangles, basically when you look at this is just a sum of many thin rectangles. Do you see that? So the rectangles that are summed over the area A1 are going to generate A1 as the area, correct? What about what happens here? If I create a rectangle here, what can you say about this rectangle? Negative, right? So because this is negative, this is positive. So you can see that over A2, because it's below the x-axis, I will subtract A2. And by similar reasoning, I will add a3. So the integral is not quite the area. Do you see why? Because if you just look at the sum, just as a product of f with delta x, this can be positive or negative. So it's no longer necessarily the area of the rectangle. It could be negative area of a rectangle. So that's one behavior of the integral. Okay?
Okay, so what does that mean?
What it means is that the integral is the signed sum of areas. So you add the areas, but you add them with sign. So that means that either if the curve is over the x-axis, the sign of the area is positive. If it's below the x-axis, the sign of the area is negative.
How does that work in the summation?
How does it work in the summation? So again, imagine the sum. The sum is if you begin from A, you will have a lot of rectangles, very thin rectangles, that are approximating A1. Those rectangles have positive height.
Okay.
But over here, all the rectangles, they're distinguished by the fact in the region A2, they're distinguished by the fact that their heights are negative. So the sum that you will accumulate is negative area, because it will be negative area of rectangle, negative height times positive width. Okay? Negative height times positive width, and that's going to be the interpretation of the integral. So if you want area under the curve, between x-axis and curve will have to be given by, can you see what I should do to the function to modify it? All I do is take the absolute value. Taking absolute value converts whichever regions below the graph to be above the graph, but does not change their shape. So that should be just the integral from AB of the absolute value of f of x dx. That's how you would measure the area. That would be A1 plus A2 plus A3. Okay. Let's try to understand other properties of the integral. So property 2. If C is a real number, then the integral from AB of C times f of x dx is equal to, I can factor out the C times the integral AB f of x dx. Now, why can I do that? The reasoning is very natural. So if you look at the integral from AB of C f of x dx, you have to realize that all it is just a glorified sum. It's a limit, but aside from being a limit, it just is your simple ordinary sum. What's the sum? The sum is from k1 to n of height of the function, which is cf xk star times delta xk. If you want to, you can make delta x all the same, so you don't have to worry about it, right? Delta x is b minus a over n, but we don't need to pay attention to those details just to understand this property. So you see, this is a sum. It just means that we have limit where n goes to infinity of parentheses c times f of x1 times delta x plus c times f x2 star delta x. Do you understand what I mean by star? By star, I mean I don't know where this point was selected. It was selected somewhere within this interval segment. And I just don't care for the moment to specify it. When you do a calculation, you will usually pick the right endpoint or the left endpoint or some other point that is very easily described through a recursive process. That's what we are seeing, right? This is just a sum, and what you notice is C is a common factor, right? So it's a finite sum, C is a common factor, so I can just pull the C out. Factor it out. Right? So this is simply, and C can be factored out to the limit. So this is C times limit as n goes to infinity of f of x1 star delta x plus f x n star delta x, which is simply C times the integral from AB of f of x dx. Make sense? Very obvious why you can factor the constant out. Let's look at property 3. The integral from AB of f of x plus g of x dx should be, you see this is just like a sum, so it should be the integral from AB f of x dx. We can even say plus or minus. We can include two rules at the same place. Plus, minus integral of g of x dx. Why does it work? Again, very simply. The integral from AB f of x plus g of x dx is limit as n goes to infinity of the sum yeah, I mean, that should be k plus minus times delta x. Now you see there is a, if you expand the sum, it's very clearly just two sums. So make sure that you see this. Which is then when you distribute the limits, just the two integrals. All right, quick comprehension check. See if you follow what happens here. Comprehension check. True or false? The integral from AB of f of x times g of x dx is the product of the integrals. True or false?
False.
Immediately false. Why? Because you will not be able to factor it out, right? The product of those two heights does not factor this way. Okay. So we know that I can break the integral into several integrals. Now notice we assumed here that A is smaller than B. Reem. 4, right? 4. What is the relationship between the integral from a to b of f of x dx and integral from b to a of f of x dx? Why? You may assume, to make this easy, that a is less than or equal than b. So you see this object, you should be able to know what to do with this object immediately when you begin, right? So if I look at b to a f of x dx, how did I proceed? I picked this point and I moved from this point. So that would be limit as n goes to infinity summation k equal 1 to n of f of, this time we start with b, plus k times what? A minus b over n times a minus b divided by n. Okay? This is the way you would proceed without thinking, I mean, you have, this is the setup, that's basically what this formula is asking you to do. Something like this. But in this case, it happens that a is a smaller number than b, right? So, in fact, when you're adding this segment, where are you moving? Where are you moving? So if you have this picture, how are you moving? If this is a and this is b, you are moving towards a, to the left. Okay? So you're going to try to rewrite this expression in terms of what it is for f from a to b. So you're going to try to rephrase this. So this is k equal 1 to n, and this is f of b, and I'm going to now change this. I'll write minus b minus a divided by n times k. And this I will also rewrite as b minus a divided by n, but then I need to put a minus. I can factor it out. You all see that? I took the negative from here, I moved it out of the sum. Now, do you recognize this limit inside of the, so ignoring the minus 1, what is this sum? This is the I can draw this sum out just to give myself some intuition. So what's in the sum is this is b, and I'm moving this way, pushing this point up, and that's going to be one rectangle. Then I'm moving this way, pushing this point up, and I'll have, so this is my first rectangle, this is my second rectangle. So I'm just drawing a schematic here. So what's happening? I'm moving like this. Now, if I were to do the same sum, but in reverse, if I were to start at A and go in reverse, what is this? This is the what sum? What approximation? Which point over each segment am I using? Right, so for each rectangle, I am using, so this is the left-handed rule. Okay? So that means that what I get is that what I have there in the negative is the same as limit as n goes to infinity minus summation k starts from 0 to n minus 1 of f of a plus k times b minus a divided by n times b minus a over n. You see what I did? I converted this rectangle just by thinking conceptually about what's happening without doing any formulas. Just thinking conceptually, I'm saying that if I have the integral starting at b, if I have this expression, then this becomes this expression with a negative. And if I ignore the negative, what I see in the sum is the left-hand rule for the function f, where you integrate it from the point A to the point B when you move regularly. Okay? So what is this? This limit is minus the integral from A to B of f of x dx. So very important property. What we just verified is that if I just invert the values, and it doesn't matter what they are, BA of f of x dx, I will get minus integral from A to B f of x dx. You see that? By just playing with Riemann sums, I am able to quickly verify this. Property 5. If A is equal to B, what can you say about the integral like this, from A to A? Or without any ifs, let's just say the integral from A to A of f of x dx. What should that be equal to? 0. Do you all see why?
No, the width is
Yeah, so if you make it as a sum of rectangles, those rectangles, all of them have 0 width. Right? Delta x always. All right. Property 6. If f of x is smaller than or equal to g of x, what can you say about integral from a to b of f of x dx when compared, so a is smaller than b here, when compared to the integral from a to b of g of x dx? What can you say?
Will be the same.
Well, g is bigger than f.
So the sum will be bigger than.
Yeah, so those rectangles have bigger heights, so intuitively you know it would be like this. And you can prove it. Okay. Seven, it follows that if f of x is less than or equal to capital M and bigger than or equal to little m, so as in this picture, so this is little m, and this is big M, the maximum, right? What can you say about the comparison? So the integral from a to b of f of x dx, what's the bigger value than this integral? Well, f is smaller than big M, but notice that, so this area within this white region is less than the area of the big box. So that is m times b minus a, and it's bigger than the small box.
When you say small box, you're referring to what's under the pink line, right?
Yes, exactly. I refer to the pink line. So thinking of areas helps you deduce properties of integrals, but it doesn't have to be. It's independent of area. In fact,
Right.
you can prove that by just applying the Riemann sums, right? Because in some cases, you can see that that the reason that the result is more general than just for area. Okay. Then property 8, I think for now would be the last property, and then we'll begin doing something new. Property 8 is that if C is bigger than or equal to A and less than or equal to B, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And the reason for that geometrically so this is A, this is C, this is B. You can calculate this integral first, so that is integral from A to B of A to C, I'm sorry, of f dx. And you can calculate the second portion separately by just counting the rectangles in it. And that would be from C to B f dx. Okay? So you think, the thing is, I said C has to be between A and B. That's redundant. In fact, without appealing to area, you should say, in fact, if C is any number, the integral from A to B of f of x dx will be the integral from A to C of f of x dx plus the integral from C to B of f of x dx. Think why. I'm going to not mention this today. But you should think why. So you see, you use this geometric restriction that's not necessarily natural. By looking at the Riemann sums, you can verify that it should be no matter where C can be placed here or there. It's always going to work out. All right, so I'm going to talk about the fundamental theorem of calculus, and that's pretty much the deepest result of this class. Deepest result, I don't know if it's hard or not. Deepest result means that, let's say, the fundamental theorem of calculus is in fact your work energy theorem. So it's the primitive version of the conservation of energy, if you think about it. The fundamental theorem of calculus is the conservation of momentum. In other words, quantity of motion is always preserved. Okay? So all those statements about basically physical statements about energy are really the fundamental theorem of calculus. They're mathematical statements. Energy, what is it? It's a mathematical knowledge. There's not so much as a fixed amount of energy as much that it doesn't it doesn't change. The net change basically doesn't change. You're always left with the same amount. You're always left with the same amount of momentum in a closed system. Those are statements that are mathematically identical to the fundamental theorem of calculus. Okay, but what is the fundamental theorem of calculus is we are tackling the following problem. So example, find the antiderivative of f of x equal to x squared. You know how to do this. Solution. What are we trying to find out? We're trying to find a function whose derivative is x squared, right? Solution. Capital F of x equal to what? 1/3 x cubed plus c, and we can say we guessed. We proved that there is that if you guess one, all the others are plus a constant. I hope you understood this proof. It was based on the mean value theorem, but we guessed, right? So now I'm gonna, just to play with you, actually, I'm gonna give you another guess. Find antiderivative of f of x equal to secant x tangent x. Do you know? Which, by the way, I'm hoping you have 2 practice exams. Just start looking at the problems there and solve them. Right? That's how you know what's roughly a third exam. You have 2 practice exams or 3. What's the antiderivative of secant x tangent x? Secant x, exactly. Again, we can guess. Secant x plus c. Now I'm going to ask you something like this. Example. Find antiderivative of f of x equal to maybe something as simple as sine of x squared. What do you think is the solution? Huh?
1/3 x cubed.
No. So actually anything, so I'll kill the tension. Whatever you're going to try to do, the answer is no, you're going to be wrong. Right? You're not going to be successful. So solution is what in hell? Does it even have an antiderivative? See? This is going to be, you can try. And how you know if you're wrong? You try, guess, take the derivative. You'll be wrong. You'll be wrong, 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 wrong. So here is where the fundamental theorem of calculus comes in. First of all, when does a function, that's what we are asking. Question. When does a function have an antiderivative? So this is our fundamental question. Okay? So first we need the following result. So you're given y equals f of x over interval AB. What is the average height of the function? First of all, does it make sense what I'm asking? Right? So I have this curve. It's a one-dimensional landscape, and I'm asking, on average, how high are we? All right, so what does it mean?
Average height computes from the minimum and maximum?
Well, I don't know. Does this question make sense? Calculate the average height. So, for example, if you are climbing on mountain, or if you're climbing on a mountain, you might ask yourself, well, in this particular vicinity where you stand, on average, how high are you, right? Because you might move a little bit and you're higher. You might move a little bit somewhere else and you stand lower. But on average, what's your elevation? Yes?
I immediately think of the rectangles in the Riemann Sum
Why?
because each of them has a distinct height, and you can calculate an average based on that.
Each of them has a yes. Well, maybe that might be precisely true, but let's build it up. So you would say, what am I trying to calculate, and how will I go about doing it? If I ask this question, on average, how tall is a student here? What would you do? Right. So here you right away tell me what to do. So this question that makes sense to you then, right? On average, how tall is the student? You will take some sort of ruler, and you would place each student against the ruler and record the information, and then divide by the number of students, right? Sum it up, divide by the number of students, you get average student height.
Can you do f of a, sum of f of a, summation of f of a to be divided by e minus a?
Well, that's what's summation of f of a, right? Right. So you work with this. So just try to picture it. So what can you do? So what you do is you cannot obviously measure all the heights. There are too many here, right? There are infinitely many heights here. So what you're going to do, you start. Notice this function is continuous. That's important, right? So continuous function. It means that if I don't move far away from each measurement, the difference in height is not really significant. So what I do is I subdivide the interval, and I start taking measurements. So here is measurement 1, and I move by equal widths, right? I move by the same width. Here is measurement 2. So this is measurement 1. This is measurement 2. This is measurement 3. And I continue in this fashion until I have n measurements. I might use b as the last measurement, right? So maybe my way of doing that is I will subdivide the landscape from A to B into n parts, I always move to the rightmost edge of each part, and I measure my altitude there. So what I do is if I stand on this mountain, I take some sort of drilling stick and I push it through the ground until I hit bedrock, and that's my height. Make sense? Mathematically, what have I done here? Mathematically, this average is, so F average is approximately, F average is pretty much approximately the summation k equal 1 to n of f of x k. Right? That's the sum of all the heights. What's missing here? The sum. What do I need to do to make it average?
Divided
By what?
b minus.
No, by the number of samples, right? I have taken how many samples? N samples. Each sample, well, first sample was taken at the point x1. Maybe I'll write this point as
N minus
x1, x2, x3, right? So I took samples at points xk, and I multiply by 1 over n, because I want to sum these heights and divide by the total number of elements in my sample size. So you have to understand this process. Make sense? Completely? What I do is this, right? So I walk on this landscape with some drill, some sort of thing that I can measure this until I hit bedrock. So I move, I drill at the right hand point of each interval. Then I move by the same interval and I drill. I move by the same interval and I drill until I get to the end. And I do that n times, where n is very large. The larger n is, the better is going to be the average. So that means that F average is approximately 1 over n summation k equal 1 to n of f a plus k b minus a divided by n. Right? No, there is no times b minus a, right? Well, that's what we have. That's the average. Now it should look familiar. So the exact average should be the limit. And I can push the n here. Now notice, I'm assuming the function is continuous. Otherwise, this process is not necessarily making sense. You see that if n is very large, then the space between the places where I picked a sample is very narrow, and therefore the function did not change too much. If it's continuous, it changes gradually. So if the distance between the two places where I picked samples is very narrow, that will, any point in between will be represented by the sample I picked. Yes?
So this is a more precise way of getting the measurements under the curve, the area under the curve?
We are not, no. Again, we are finding the average height of the curve. Average height. How high on average is this curve? Okay? We're getting a formula for it.
This is going to relate to the antiderivative?
Yes. It's going to.
Be like a formula?
It's gonna relate to the antiderivative, but what's important here is that you see it. It's a concept, right? I mean, formula comes naturally if you see the concept. You understand? All I'm doing is I'm just walking in this one-dimensional landscape and I'm just picking samples. And then I know what to do. You're familiar with what average is. So I just take that ordinary average. Now, looking at this formula, this looks very familiar, but to make it very familiar, something must be changed. Look at this formula. It looks very familiar, doesn't it? Or should look very familiar. What should I change so this is indeed familiar?
You're missing a b minus a.
Yes, you see, this is 1 over n, but I want to see b minus a, right? So what I do is I modify, and let me, in yellow, I'll write what I modified here. So I can modify this thing and put here b minus a. But if I place b minus a over there, I have to divide by b minus a. And then what I am obtaining, is that this is just 1 over b minus a integral from a to b of f of x dx. So that is my formula for the average. What I do is I will integrate and divide by b minus a. Okay, very important formula for what we are doing here. So, observation. This is just a check if you actually say something there, right? So if f is continuous, or let's even do that comprehension check. Not a trivial comprehension check. So find limit as h goes to 0 of one minus h to 1 plus h of two x squared dx times 1 over 2h. Can you do that? And there is no calculation involved, right? What it involves is understanding what's asked here, right? Think of limit of h goes to 0 as h being, let's actually make h go to 0 from the right. So h is very small, okay? So what I have is I have a landscape. The landscape is y equals to 2x squared, right? If h is very small, where am I standing on this landscape? So if h is very small, so somewhere over here is 1, somewhere over here is the point 2. And if h is very small, This point is 1 minus h. This point is 1 plus h. Now if h is very small, what is this calculating? What is this calculating, first of all? This is calculating the average elevation on which I stand. So what would be the answer in the limit? So h is getting smaller and smaller. What's the average elevation?
0.
No,
630.
not indeterminate. If h is very small, what happens? H goes smaller. What happens to this curve?
It's 1, 2.
What's the answer? Not 0. Where is 0? All the heights that you're adding up are positive. So what's the answer? 2. The answer is 2 without any calculation. What I'm trying to make you understand is, you see, you take the limit. But what are you asking? You're asking without the limit. You're asking this is the average. You should be able, but when you go home, derive this formula. Understand why this formula works. This formula that we have come up with is the average elevation. Now, if h is very small, then where I'm walking is very close to 1. The function 2x squared is continuous and very close to 1. Its elevation is very close to 2. So if h is really small, the average has must itself merge to 2. Make some sense? All right.
Wait, how would you do that from the formula? Like what?
Because I read the formula, I'm just saying what's supposed to happen, right? I'm not doing any calculations at all. I'm just thinking, what is this? This formula represents the average, which I just derived what it is, right? So if you understand from this point that I just took a bunch of samples and then I converted it to a Riemann sum, and then I converted the Riemann sum to this formula, right? So this formula now is the same as the average elevation. Now, what should be the average elevation near a point of a continuous function? It should be very similar to that point. Okay? I'll try to explain it more as we go along. I hope to at least cover the fundamental theorem of calculus somewhat today. So the solution is that it's 2 near if x is near 1, 2. So the average is near 2. So here is what we do with the fundamental theorem of calculus. So if f from AB to R is any continuous function, and that's very important, continuous function, then f has an antiderivative. say a function of this form is going to prove useful, capital F of x, where what you do here is you start at a, let's say, and end at x, and then you write the function using a different variable, f of t dt. Now here is why. So here is a continuous curve . Let's actually call it. So there is a reason so that it will cause some confusion if we don't switch to another letter. So instead of x, we will switch to t. So let's say this is the t-axis. This is the y-axis. So even if your function was given as y equals f of x, just switch the variable to t. I will try to explain why in a moment. Okay. So this is the total graph from a to b of the function f of t. Okay. So let's try to understand the following function. So your nice aunt baked you a one-dimensional cake, or even less than one-dimensional. But that's there. Yeah. So baked you a two-dimensional cake, I guess. I mean, if you consider the area here, right? So then you have one slice is made at A for the cake, and the other slice you pick. So you decide where to cut the cake. Okay? And that point where you decide to cut the cake is x. So you decide to cut the point at x, okay? So f of x represents how much cake you get, right? Think of f of x as how much cake. Now, in particular, this f of x is the total, because it's two-dimensional cake, the amount of cake is given by its area, right? So that's the area of cake from A to the point at which you decided to cut. And because the point at which you decided to cut has nothing to do with the function, you want to represent this as f of t dt. You don't want this x and this in the variable of the function to vary together. So you switch variables. If we have time, I'll explain more about what happens there. Okay? So let me ask you, let's see what happens if you're saying your auntie is a little autistic, so you say, auntie, f of a. What are you telling her?
She should not give you a cake.
Exactly, you're insulting her. Don't give me a cake, auntie. F of a is 0. You get no cake. Understood? F of a is at least one easy value where you don't get a cake, right? Now, what happens if what you do is, the idea is, I mean, it's just a very clever geometric idea. Suppose that what you do is you just vary x a little bit, right? You want to see what's going to happen if you vary x a little bit. So I'm going to exaggerate, so this would be x plus h. So x with a perturbation. So you varied it just a little bit. I want you to express this region that I enclosed here, this region here. So what is this in terms of my function? What is this in terms of f of x, this region? How do you get there? So you want your aunt to give you this region. You understand? Your aunt can only give you the left portion of the cake. And that's your aunt function f. Right? You want your aunt to force you to give you this middle region of the cake. How are you going to communicate?
F of b minus f of x plus f of h.
F of b minus what?
F of x plus f of h.
Well, actually, you have so f of b minus f of x will give you this region, plus f of x will give you this region again. So not quite.
But just h.
So I just want this region. So what you said f of b, give me the full cake. And then you said subtract f of x, subtract this part. Now you have this part of the cake. And then you said add plus, I forgot what you said. No, but if you just h here will not be the same as x plus h. No, so that's incorrect. How do you communicate? Give me this region, please.
A plus x in parentheses plus h.
Sorry?
A plus x in parentheses plus h.
No.
H.
No. No.
You say f of x gone, and then you say that not f of b gone, but this right part should be done.
No. No?
Then you create another one.
Delta x.
No, you can go to h.
You have this function f, make your aunt give you this region.
Take a whole function in there.
The cake is getting cold.
No, take a whole function.
Okay, so take a whole function, okay, here,
Yeah,
and
minus.
minus.
And from b to x plus h and then minus x to no?
Very simple. I'll put it in red so you see. So what I do is f of x plus h minus f of x. Now you have it. So it means give me this cut minus this cut. That's it. You have it. Okay? Now what is that going to be? F of x plus h minus f of x. It's going to be the integral from a to x plus h f of t dt minus the integral from a to x f of t dt. I can express this as one integral. What's that one integral? You can also look at the picture there. You can see what the integral is.
From x to x.
It's the same as the integral from x to x plus h
And also be 0 to
of f of t dt. That's this region. Okay? Now let's look at this region a little bit more carefully. I'm just going to blow this picture out. And then see what happens if you make h smaller and smaller and smaller. So here is that this point is x. Look what happens if I select h very small, right? So if I start selecting h smaller, so I have this region. Now, very small x, very small h. This shape, it's exactly this is almost the same thing as as this shape, which is a rectangle. Do you see that? If h is very small, I almost have a rectangle. And that's for a continuous function. If h is very small, the integral, I should put it, I guess, here. I'll write that this thing is essentially the same thing as f of x, this point, times the width. The width, this is from x to x plus h, so the width here is h. So this is essentially the same as f of x times h, and that's if h is small. Do you see that? So this region is essentially a rectangular region whose height is x. Okay? So as a consequence, what we have is that limit as h goes to 0 of f of x plus h minus f of x divided by h. This is going to be the same as limit as h goes to 0 of f of x times h divided by h, which is f of x. So I'm not sure if you lost me. What we have shown is this. We have shown that if y equals to f of x is continuous, and notice here I have y equals f of x, and I define the function capital F of x to be the integral from any number a to x. And notice I switched variables to something else, f of t dt. Then the derivative f prime of x is equal to limit as h goes to 0 of f of x plus h minus capital F of x over h, which according to this calculation is little f of x. So we have shown that this is an antiderivative. Hence, f of x equal to the integral from a to x f of t dt is an antiderivative. Of little f of x. Let me give you a few examples. So find antiderivative of, remember this function that I mentioned? So we had sine of x squared. So the solution is very simple now, using this notation. Solution, the antiderivative has to do with area under the curve. Solution, if I take capital F of x equal to, say, integral from 0 to x, and here I write sine of anything other than x squared, so it has to be t squared, let's say, or another letter so that it's not the same value. So if we have this, its derivative is sine of x squared. And therefore, all antiderivatives of this function can be written as this integral plus c. So example, find antiderivative for f of x equal to x squared using this new notation. We actually observe that if I take capital F of x equal to, let's say, 0 to x of t squared dt, which is the same thing as 0 to x of, you can replace t, this is just a dummy variable, u squared du, anything other than x satisfies f prime x equal to x squared, which implies that the integral from 0 to x of t squared dt, because we know all antiderivatives are of a particular form, it must be of the form 1/3 x cubed plus c. So this function, although it has this complicated expression, in fact must be 1/3 x cubed plus c. What particular value? Well, we can know that if I plug this lower bound 0, f of 0 is 0, that would be c. So in fact, 1/3 x cubed is equal to 0 to x t squared dt. Okay? They are actually representing just two representations of exactly the same function.
So how would you know which one's the right?
No, I mean, any antiderivative is this plus a constant. The thing is, this form of an antiderivative is ubiquitous. It always works. Right? For any continuous function, this is an antiderivative. Sometimes you're able to guess a simpler formula for it. Okay?
Sorry.
Any continuous function, so just here as an example. So without thinking, you can always come up with a very easy form for an antiderivative if the function is continuous. So if I have the function f of x equal to, say, cosine of x squared divided by 1 plus x squared. This function, if you want to find antiderivative, if you want to find antiderivative for this function, you can just say f of x equal to any number. Let's say pick here -1. It doesn't matter what this number here, all the way to x cosine of u squared. You have to switch the variable over 1 plus u squared du. Then the derivative of this function is cosine x squared over 1 plus x squared. Do you understand what happened here? So I was not able to come up with a simpler form of an antiderivative, but I was able to come up with some form of antiderivative. Okay?
So if I did that for like a simpler form, like x.
There was one student, one time I was not careful enough in phrasing the exam, and he was smart enough to realize that all antiderivatives can be written this way. So in fact, he solved many problems by just doing this. You understand? By just modifying x to another value, just a number to an x, and that was an antiderivative, right? This is always correct. The thing is, this formula, you see, this is a much more useful formula. 1/3 x cubed is much easier to use than this expression, but they mean exactly the same thing. See, that's what I mean. How I need to know that all the antiderivatives I found are of a particular sort. So that's how I know that this odd creature has to be 1/3 x cubed. So let's see. Give me a few more minutes. So here is application. Let me just write this application, and then we'll go. So application, suppose you wish to compute the area from A to B of f of x dx. If this is abstract, imagine that what you're trying to do is you're integrating from 0 to 1 x squared dx. Okay? You can use Riemann sums, but let's try if we can do something better. Suppose you wish to compute this thing. So notice that the integral from A to B of f of x dx is just capital F of B, where f of x is equal to the integral from A to x of f of t dt. You see the same exact function, but I just modify this and make it x. This f is, so this f satisfies f prime of x equal to little x. So it's one antiderivative. If g is another antiderivative, if g is another antiderivative, then g of x has to equal to or better, f of x is the function that I need to come up with. F of x has to equal to that other antiderivative plus a constant. Does it make sense? Remember, all antiderivatives are very similar. So in this case, I have this formula for the antiderivative. So I have this complicated formula for the antiderivative. Here it is. Right? Suppose I was able to guess an antiderivative of the form 1/3 x cubed. I'm able to bypass this formula and find an antiderivative of this form. So what happens then is I can figure out what is C, and then I have another formula for F. So in particular, I plug in A. So we have that 0 equals to F of A, which is equal to G of A plus C. And therefore, C is equal to minus G of A. And the conclusion is that this function is equal to the antiderivative minus the antiderivative at A. Let me explain what this means. Give me 2 minutes. I'll show you with examples. You will appreciate what we have just established. Example. Suppose what we are trying to do is you are trying to find the integral from 0 to pi over 2 of cosine x dx. Okay? So then what you observe is that capital F of x, instead of this area problem, you find capital F of x, and that's the integral from 0 to x cosine t dt. And what you want to compute? F of pi over 2. You want to compute f of pi over 2. But we can guess g of x, antiderivative of this function, it's what? Antiderivative of cosine is sine. So sine x. So according to what we just derived, we have that the integral from 0 to x of cosine t dt is equal to sine x minus sine of 0, which is equal to sine x. In other words, I figured out that this function is sine of x. So now, therefore, the integral from 0 to pi over 2 of cosine t dt, without using any Riemann sums, I can just right away figure it out to be sine of pi over 2 minus sine of 0. If I find antiderivative of this function, I'm able to take that antiderivative at the endpoint, subtract antiderivative at the first point. Okay? So this you need to think about, practice. It will be on Friday's exam. Not this Friday, but next. 19.
Oh, that's a Friday.
That's a Friday, right? All right. You can go home.
Are you going to talk more about this?
Yes, I'm going to talk more about it on Tuesday, but you see this thing. If you're living like, oh, whatever, I don't care, then what you're going to see on your grade is, oh, whatever, I don't care. Next, I'm going to simplify it. In other words, I'm going to show you how to work it technically, but what I want from you is to understand why this works, right? Yeah. Goodbye.